Okay. So I assume everyone finished method of joints on this one from Wednesday? Brendan, your eyes are telling me that you didn't.
I did a little bit of it, and I got bored and I went to something.
Oh, all right. Well, it's on you. Okay. So let's do this one.
We can't see what you're talking about.
Well,
We can't read
details.
lines. That would be fun though.
Flip the page over, and let's look at 644. Okay. Determine the force in members BE, that's this one, EF, that's this one, and CB, that's that one. Okay? Yeah, well, you'll get there in a second. 644. Yep. Okay. Last page on the back. Anyone have a recommendation from looking at the last page on the back how we should solve this guy?
Can we cut?
Oh, yeah.
We could cut it, right, and do a method of sections without even doing reactions, potentially, right? We could just cut this guy and say it's in static equilibrium, and then look at the top, because it's got forces applied on it.
What's the max number of beams in copper?
3.
Cool.
Yep. Because the max number of equations you can get in 2 dimensions is 3, right? Some of the forces in the x and the y, and some of the moments about a point. All right? So if we do that, we should probably draw a new free body diagram. It's going to look like this, right? We still have all the loads. Got to make sure they stay on there. 5, 10, 5. We'll have CB, EB, and EF, like so. And then we can just write our equation. Sum of the forces in the x has to be 0. What do we have acting in the x? Yeah, plus 5, plus 10. Yeah, minus some part of EB. And it looks like this is a 4, 4, so that means we're at 45 degrees. So it'd be minus EB cosine 45 degrees, we'll say, equals 0. So we actually solve for EB right off there, right? It's just 15 divided by cosine 45. .2 kilonewtons. Okay. We can sum the forces in the y direction. What do I have acting in the y? -5. Minus CB. Minus 21.2 sine 45. Minus EF equals 0. Okay, I've got 2 unknowns still. I can't solve it, so I'll go for a second equation and I'll sum the moments. Where would you like to sum the moments about? E. For show, right? Because if I sum the moments about E, I cancel the one that's got an angle in it, and I cancel EF and 5, and I'm just left with CB. So this is going to be pretty straightforward. If I sum these moments, counterclockwise is positive. I actually cancel the 10 too, so I'll just have 5 times 4 in the negative plus CB times 4 in the positive has to equal 0. I'm not a rocket scientist. Played one on TV once, but I'm not. CB is going to be what? Right? So then I can take that, substitute it back up in here, and we can figure out what EF is. Is it?
That's what I got.
I'm hearing 25 from the audience.
24.99.
Okay. Method of sections. It's our friend. All right. So, let's look at the second part here. 645 says determine the force in members BF. That is this one. BG. That is this one. And AB. That is this one. Does anybody see a way I can do this without doing method of joints?
You could also cut along the curve.
Well, if I cut along a curve, though, how do I do that without cutting through 4?
Just stop before you get through the last one.
Just stop. Yeah.
You could cut between the first and second block, so through A, B, A, G, and then through that, and then go back and solve for B.
So I could cut through here,
Uh-huh.
and then go back and solve by method of joints at F.
Yes.
That's a good idea, right? So that's something that on the exam people did when they realized they had to cut through 4. They said, well, why don't I cut through the 3 that I can, and then go back and use what I find for FG to solve for BF. There's an even more direct method here. Yes?
BF is a zero force method. Nothing to cancel that out.
Yes. BF is a zero force member, right? Says the Middle East, because F here has no load applied to it. 3 members, 2 of which are collinear, so the third is a zero force member. So then we can just do the cut across here and solve for the 2 remaining ones.
FG also equals to EF.
Excuse me?
FG is also equal to EF.
Yes, FG is also equal to EF. All right. Okay. Let's keep going. I think I have another chapter 6 in here that's maybe a little. We got machines to work on for a while, right? Got to do some machines. Ah, yes. Nothing better than personal hygiene, right? Please don't examine my fingernails right now. They're very dirty.
Oh, jeez. Oh, that's gross. Why did that?
Been working on a car. Sorry.
Turn them down. Use those nail clippers.
Well, but then you can't scrape gaskets off as easily.
That's fair. Just use your toenail.
Gross. Ah, that's disgusting. All right. We've got some nail clippers. I did this one because it sparked such interesting conversation. Scintillating. Okay? How can we tell that this is a machine and not just something that we can sum the moments and take the forces about? It has multiple parts, right? It's got connections in it. The force is applied in one location here on 2 different bodies, and then it's the action of the force is over here on some different ones. Okay? So where the force is applied to the unknown that we're interested in is on multiple bodies. Okay? So when we have this, we typically need to draw a free body diagram. So let's do that. We're going to have one part of our nail clipper. We'll have another part of our nail clipper. And one more part of our nail clipper. Okay? And it looks like the forces on this, I should make this one just a little bit longer probably, are 1 pound here, 1 pound here, right? And then we'll have, assuming the blades are pin connected at B, back here, and the surface at D, that's right here, is smooth. Determine the normal forces on the fingernail when a force of 1 pound is applied to the handles as shown. The pin AC slides through a smooth hole at A. So these smooths, right, are key because that tells us that right here I've just got a vertical normal force, which means I've got a vertical equal and opposite force there, that this will be in D. Right? Everybody okay with this? And then it looks like at A, there must be some normal at A acting down on the tip of the handle, right? And then the equal and opposite of that would be the normal at A acting up, because it's a smooth pin or two-force member, if you want to think of it that way, that goes through the hole and acts on the bottom. Okay. So I think we can actually solve for in this top one. We can say that the sum of the forces in the Y has to be equal to 0, and so we'll have 1 pound down minus NA plus ND equals 0. Okay, two unknowns. We're going to have to write another equation. I'm going to suggest we sum the moments, and let's sum them about D and set those equal to 0. Okay, so about D, I'll have NA times 0.25 inches. Oh no, my pen is dying. Minus 1 pound times 1.5 inches. And this has to equal 0. Man, is this one dying too? Jeez. So we can solve for NA. Right? It'd be what? 1.5 divided by 1/4, so times 4 be 6.
Yes.
Okay. So if NA is 6 pounds, we know, okay, 6 pounds here. We know we could solve for ND then if we wanted. ND, if we stick that in, is going to have to be 7 pounds. Okay. Then let's come down and look at this guy. At the bottom of this guy, we're going to have some normal of the finger, we'll call it. Right? And we can do the same thing. Sum of the forces in the y direction has to be equal to 0. So we'll have 1 plus 6 minus the normal of the finger equals 0. So we're going to go with, hopefully the normal of the finger is 7 pounds. £7 of fingernail slicing action.
So there's no forces at B that we care about?
Well, we put the 1 pound on it.
Right. But isn't there a BY? Keep the top and bottom part together?
Isn't there a BY?
Is this pin connected at B?
Thinking.
Buffering.
Yeah, you could say that there's a if we put a normal at B down here, then we could let's sum the moments then about B and set them equal to 0. Okay, and we'll take counterclockwise as positive. We'd have 6 times 1.5 in the negative plus the normal of the finger times I'm sorry, that wouldn't be 1.5, it'd be 1.75 plus the normal of the finger, which would be 2 equals 0. Tell me what normal of the finger is equal to. Now I'm getting upset.
We still have to find 7B. How come B would be smaller than 7B?
Okay, let's do this one then. 'Cause now I'm annoyed. If we determine the normal at D is 7 pounds, right? So normal at D, we'll have 7 pounds down. And say then this is normal at B. This is the normal of the finger. This distance is 0.5 and this distance is 1.5. If I sum the moments about B in this one, I'll have 7 times 1.5 minus normal of the finger times 2 equals 0. You solve that one, do you also get 5 1/4?
Yeah.
Thank you, Brendan. Right? I neglected to do a good free body diagram, and so I neglected to get the right answer. Sorry, I make that mistake sometimes. I know you guys never do. Okay, so I neglected to put my normal at B on here, which I needed to do, and that allowed me to jump to a conclusion here that was not good, because when I sum the forces in the Y, I just put in the normal of the finger, when in actuality I also had the normal at B equals 0, which this would have led me to correctly write the sum of the moments about B to figure out what the normal of the finger is. And I convinced myself that this was right, because then I was upset and I said, well, let's do the same thing but on the top blade. And it turns out that the normal of the finger is also 5 1/4 there. And so by doing it in both locales, I'm going to get the correct answer.
But it turns out that we can actually need the top blade. We could have done it without it.
Yeah, you could have done it without the top blade. I just did it to check myself because I'd already wrecked myself.
Yeah, I searched it up online. It was 5.25.
Can't get away with anything these days with the old internets. Okay.
Guess we probably caught up with the work.
No.
All right. Okay, I have one more here that from chapter 6 that I wanted to do. It's near and dear to my heart. Okay, 6-100.
Oh. Yay.
Operation of exhaust and intake valves in an automobile engine consists of the cam C, push rod DE, rocker arm EFG, which is pinned at F, and a spring and valve V. If the compression in the spring is 20 millimeters when the valve is open as shown, determine the normal force acting on the cam lobe at C. Assume the cam and bearings at H, I, and J are smooth. The spring has a stiffness of 300 Newton meters. This is a really long problem introduction with a complicated picture to make for actually a very simple problem. Okay? Who can help me simplify this? What free body diagram do I likely want to draw? The rocker arm? Probably a good choice. So the rocker arm looks like that. Okay. What forces act on the rocker arm? Okay, so yeah, there's going to be some DE, FDE. This is the force of the push rod. So the push rod is this thing here. How this functions is the camshaft in your car spins around, and it's got what are called lobes, or if it weren't on a camshaft, it'd be called a cam, and it's just something that's off-centered that as you spin causes an up and down motion of this member ED, which is a two-force member. Okay, so as this spins, it pushes this guy up, which goes to the rocker arm, named that because it rocks back and forth. Okay, and it then in turn moves this valve up and down. Okay, the spring holds the valve springs hold the valves shut, and then they're only opened by the force of the camshaft coming through the rocker arm and pushing this down. Okay,
Sure.
so I'll have FDE. What else will I have? Yeah, so I have to counteract this force of the spring that's pushing up on it. Anything else acting?
Pin connection or F?
Yeah, there'd be a pin connection at F. So I'd have F sub X and F sub Y, right? But we're asked to determine the normal force acting on the cam lobe at C. So we're just asked to find FDE. That's all we really need to find. We can do this with one equation, right? Yeah, Vlad's got it. Sum of the moments. Where should I sum the moments about, Vlad? Yeah. It's got to equal 0. Counterclockwise is positive, so I'll have FDE times 0.025 meters minus Fs times 0.04 meters equals 0. I lied. We need to determine Fs, which is going to take a second equation, right?
The force of the spring then.
Yeah. Force of the spring is just Ks, 300 newtons per meter. So then we just need to figure out how much it's deflected, and it says it's deflected 20 millimeters. So 0.02 meters. I think that's, is it 6 newtons?
Yes.
Okay. So I can substitute that back in here and solve for FDE. I think it's going to be like 10 or something crazy like that. 9.6? 9.6 newtons. Okay. Okay.
Spring? No.
All right.
Six newtons, we're doing faster.
Okay, I think that's all our machines, yes? I think we did all our machines there. The trick to machines, if the force is applied in one location and you're solving for its output in another location, and there's a pin anywhere between, it's a machine. Okay? If there's more than one member, it's a machine. All right. So then we went to this, right? Shear and moment diagrams.
Andy, can we do it equation way and picture way?
Yes, please.
Yeah, we can do it both equation way and picture way. All right? Let's do it the picture way first because it's more fun. Okay? What's the first thing we have to do when we're going to do a shear moment diagram? We need reactions, right? Okay, so in this case, I have a triangle and a rectangle. So the triangle, it's going to be the force underneath the area underneath the load distribution curve gives me the total force. So that's going to be 3 kip feet times 6 kip feet, 18, but then I divide by 2 because it's a triangle. So I'm going to have 9 kip feet, or 9 kip, right? And that's going to happen 4 feet over from the skinny end. Okay. My 2 kip foot distributed load is going to give me 6 kip, excuse me, right smack dab in the middle. So I can sum my moments. Oh, let's sum them about A. and say they're equal to 0. It's by, sorry. So it looks like I'll have negative 9 times 4 plus by times 6 minus 6 times 7.5 equals 0. The by is 13.5 kip. And we had a total of 15 there, so that means that AY is going to be 1.5 kip. Okay? So, if I do the moment area method, my dying blue pen, what does this cause me to do? It jumps up 1.5. Okay? And then nothing happens until I get to the 9, right?
No.
That's not right. It's very not right. You should not agree with me. Yeah, it goes down with the slope of 3 kip per foot, right? Okay? And it has a total change of what? 9. Okay? So I change the area underneath the curve as I go to the right. So as I go over to B, I'm going to go down 9. Okay? And it's at a negative slope. I don't just say, oh, nothing happens till I get to 4 feet and then I jump down 9. Okay? I understand why some people make that mistake, but I'm telling you, you're wrong. If you make that mistake, it's an absolute truth. We don't need to debate it. You're wrong. Okay? So do the downward slope with a total change of 9. So if we have a total change of 9 starting at 1.5, I believe that means we'll get to negative 7.5, right? Okay. At by, we jump up 13.5. Okay. So if I jump up 13.5 from negative 7.5, I think I get to 6. Whoa, this is whoa. This is wrong.
It's quadratic.
Is my slope constant?
No,
No, it's quadratic. It's a curve. So I have a slope of 0. Let's get rid of this guy. My slope is going to be 3 down here, sorry. And I'm going to go from a 0 slope to an increasingly negative slope. Woo! Thank you, Brendan. Man, what is it with me today and leading you guys astray? It's just like I'm messing with you right before the final. That's what all the cool teachers do. Okay?
What is that?
All the cool teachers. Yeah. Now what do I do? Now I have a constant slope of down 2 over 3 feet, total change of 6,
so it'll just go
and I end up right here. Okay? So my moment diagram would look something like that. Or excuse me, my shear diagram would look something like that. Now, we like the moment area method until we get to a triangle load like this. We can handle that up through the shear diagram, but can we do it now in the moment diagram? Not really. I mean, we'd have to figure out where the intersection is, and we'd have to find this area, and it's exactly why I put this one in here, okay? Because we need to practice doing the analytical method, okay? And so to do that, how many regions do we have of loading here? We have 2. 1, 2. Okay? So let's draw a free body diagram of this guy in region 1. In region 1, I'm going to start, got this slope that goes up. I've got a reaction of 1.5 here. And then I probably need to put some shear and moment on it. How do I decide which direction to do the shear and the moment? Okay, for the moment, I like happy beams. Digas feliz. Happy beams.
Not as good as Cuerpo Libre.
Not as good as cuerpo libre. Okay. Then the shear should be what direction? So it makes clockwise rotation. So in this case, that would be down. Right? Okay. And we know that this cut is a distance x from the end. So if I sum the forces in the y direction and set them equal to 0, it looks to me like I have 1.5 minus v minus, man, minus what? Okay, we have a rise of 3 kip per foot, or 3 over a run of 6. So the slope of this is 0.5x, right? Or the magnitude of this is 0.5x. The slope is 0.5. Right? The magnitude of the distributed load is just 0.5x. And I got that because I know by the time I get to 6, I have a magnitude of 3. Right? So the rise over the run, 3 over 6, gives me 0.5, which is the slope of this line. So then the magnitude of this guy is going to be 0.5x. Right? So then if I wanted to find the total resultant force here, which maybe I'll call Fr prime, it's going to be the distance x times the magnitude 0.5x divided by 2, because it's a triangle, right? And that's going to equal 0. So let's...
where the 2 on the bottom comes from mathematically?
Yeah, because it's the area of a triangle, which is 1/2 the base x times the height 0.5x. So it's 1/2 base height. In this case, the base is x, the height is 0.5x. Okay? So then let's solve this equation for v. We get v is equal to 1.5 minus, let's see, 0.5 divided by 2 is a quarter, so 0.25 x squared. Okay? So that should be the equation of this line here. All right? Then let's do the moment. We always sum the moment when we're looking at a beam about where? The cut. Okay. So we'll have the moment minus 1.5 times x, right? Plus the magnitude of the force, which we decided was 0.25 x squared, right? That's what we decided above, times its distance, which would be x over 3. It's going to equal 0.
Y over 3.
Yep, because the distance to the resultant force is 1/3, 2/3, right? So it'd be x over 3.
And where did the 1.5x come from again?
The 1.5x comes from I'm summing the moments about the cut, so I have 1.5 going up, and it's x distance away. So then I can say, well, my moment is going to be equal to negative, a quarter divided by 3 is going to be like 0.0833. 0.0833 x cubed plus 1.5 x.
Nice.
Doesn't that look beautiful? So let's try and plot this moment here. At 0, it would be 0. At 1, it's going to be positive, right? Because I'd have, at 1, I'd have negative 0.033 plus 1.5. So it'd be like 1.4. Right? At 2, I'd have 4 times 0.0833. It's a small number. Think what I'm going to have, right? If I look at this, I know my slope is positive, but decreasingly positive, and going to some point of inflection where the slope would be 0. So I think I'm going to do something like that. Okay? And then I'm going to start going down because I have an increasingly negative slope here. So then I'd need to figure out the area of that, or I could just try and plot this. Let's see where I am at x equals 6. If you stick in 6 here, what do you get? Substitute in 6 for x. Negative 8.99. Fair enough. So by the time I get over to here, I'm at negative 8.99. So it does something like this. I don't know. Okay. That's comforting, because remember, if I go back to my area moment method, remember that the change in the moment graph is the area underneath the shear graph. And this, if I recall correctly, this is 3 feet, and this is 6. So the area underneath that would be 6 times 3 divided by 2, or 9, and it's positive. So that means that I'm going to then have a very positive slope that's decreasingly positive, like that. Okay, and my graph would look something like so. Okay. So I did a hybrid there. Let's finish the problem using equations. So let's draw our second region free body diagram. Which is going to look like this, where I have 13.5 up here, 1.5 up there, distributed load like this, and then distributed load like that. Okay. I'd still want a happy beam, and I'd still have my shear force down. Okay. So then I can sum the forces in the y direction. This time I can say, I just know what this is. It's 9 because it's the whole thing. And it's located 4 from here, or 2 from here. Okay. So some of the forces in the y, I'll have 1.5 plus 13.5 minus 9 minus, this has a magnitude of 2 kip per foot. So minus 2 times, if this distance is x, what would it be multiplied by?
X minus 6.
X minus 6. Exactly, Michael. Good job. Okay. Minus v equals 0. Or v is equal to 13.5 plus 1.5 is 15, minus 9 is 6. So 6 minus 2x plus 12, or 18 minus 2x. Which that corresponds to this, to our chart here, because 18 minus 2x at 6 across would be 6 with a downward slope of 2. Okay. Then we can do the same thing, sum the moments at the cut, and set that equal to 0. Summing the moments at the cut, I'll have the moment at the cut, I'll have some resultant here, which I'll do my f prime resultant. So plus, that f prime is going to be the magnitude of the force, which we decided was 2x minus 12, times the distance, which would be, x minus 6 divided by 2. Everyone, where's x minus 6 divided by 2 come from? Because it's in the center of this rectangle. This distance is x minus 6. So that would be x minus 6 divided by 2. I'm sorry, this distance is x minus 6. This is 6. This is x. So x minus 6 is here. X minus 6 divided by 2 gives me halfway across, which is where that resultant force would act. Plus my 9 kip times the distance to this. What would the distance from the cut be for my 9 kip? Vlad's got it. X minus 4 minus 1.5 times x equals 0. And this right here is maybe the first time I feel good about the fact that you had to learn how to expand polynomials. Right? This is the first time I've recognized a use for the expansion of polynomials, let me think, ever.
You just use a calculator.
Right? You guys remember learning those? Good times? Expanding polynomials?
I remember doing them, but I don't remember how.
Oh, sure you do.
No.
First inside, outside, last? Mm-hmm. Okay. So it'd be 2x times x minus, you can figure it out. Okay? You can come up with an equation here.
4.5x minus x squared.
That is, apparently, m equals 4.5x minus x squared. Is that what you said?
Told you a calculator can do it a lot faster.
I'm sure a calculator can do it a lot faster. Okay? And there you can get your plot.
What calculation did you use?
Solve. And then expand to make it look like this.
Okay?
Otherwise it's factored.
So you solve for x and then expand? Yeah.
Questions on these? You should practice these. They'll be on the final. Guarantee you, I will give you a shear moment diagram on the final. Okay?
Distributed load.
Can you imagine what it would be like if I gave you on the final one that looked like this?
I can imagine. average.
Right? This would be some, you know, like x cubed function, right? That would not be pleasant. But does everyone remember how you find the location of the resultant force in this guy? What did we determine last week? Or on Wednesday?
It's the integral.
Yeah, it's an
times
integral.
x divided by the integral. But if you gave us one like that, finding like my cut at multiple sections and the distance is really wonky.
Yeah, it'd be really hard.
You can just make.
I won't give you one that's greater than a triangle.
You're not gonna give us calculus stuff?
I'm gonna give you calculus stuff, but I'm not gonna make you. I'm not saying you don't need to know this. I'm saying I will not ask you to find the shear moment diagram of a second order load function. Okay, so I will ask you to find the shear moment diagram of one that's a triangle, which requires calculus. Okay. Well, it doesn't really require calculus, I guess, but it requires you really know what you're doing. Okay?
Figure it out.
Yeah.
Does everyone understand that you're going to have to do a triangle load shear moment diagram?
Triangle shear moment.
So I really recommend you practice the triangle shear moment diagram. Okay? That's going to be a hard question.
Anything else you want to recommend to us?
Anything else I want to recommend? Not yet. I'm not there yet.
Imagine truss.
Yeah, a truss or a machine? Sure. Yeah, I'll give you a machine, right? Because I'm definitely going to give you a machine because you guys did not do well on the machines last time, and I'm not doing that to be mean, but it's because it's something you need to know, right? And so I'm just going to guarantee, if I tell you I'm going to put a machine on there, that's going to make you study it, so then that makes sure that you know it, and everybody's happy, right? I didn't say that. I said I'm guaranteeing a machine problem and a sloped shear moment diagram problem.
This one's gonna be 6 problems?
You know, 6 to 10.
What?
No.
So we can pick 6 out of 10?
No. I have not written it yet. Okay? So, yeah. I got a request, email request for me to do a problem, so I'm going to do that one now. It's 8:30 in your book. Okay?
What if we don't want to grab our book and look?
I'm going to pull it up for you. Put it on the screen here. It's a friction problem. There will be friction on the final. Okay? So I'll freeze that so you can get it in your notes. The problem we're going to do is 8:30. We've got these two blocks, A and B. They're connected by a spring. Okay, where K equals 2 pounds per foot. A weighs 10 pounds, B weighs 6 pounds. They're resting on an inclined surface for which static friction is 0.15. Well, let's see, mu static for A is 0.15 and mu static for B is 0.25. Determine the angle theta for which both blocks begin to slide. Also find the required stretch or compression in the connecting spring for this to occur. The spring has a stiffness of K equals 2 pounds per foot. Okay, so what type of friction problem is this? 2, right? It says for them to slide. So we're right at that point where things are going to start moving. And so if that's the case, what do we know? We know that we are at where the force of friction is equal to the force of friction max, right? Because it's a type 2 problem. So let's draw separate free body diagrams for each of these. See if I can get another black pen here. Okay. So at A, I'll have 10 pounds going down. I'll have the normal at A. We're tilting this guy up, so that means that the block is going to slide down, so the force of friction is going to act up, right?
Mm-hmm.
And it will have a magnitude of what?
NA times 0.15.
Yep, 0.15 in A. Okay. And do you want to assume that the spring is in tension or in compression? Yeah, I'm going to go with tension as well, right? I think it's pulling on B. Okay, so we'll put F spring this direction. At B, then, we have the force of the spring pulling it down. We have 6 pounds going down. Force of friction's also going up on this guy and will be 0.25 in B. Okay. Everybody good with this? Okay. So let's rotate our coordinate system. Okay, so that we can look at the problem like this. It's going to make it so that we have less trig in the problems. Right? So now I can say sum the forces in the x direction. And I'm going to look at block A first. Okay, so for block A, in the x direction, I'll have minus 10 sine theta, right, where this is the angle theta. I'll have plus the force of the spring plus 0.15 in A equals 0. So it looks like I have 1, 2, 3 unknowns. So let's sum the forces in the y, set that equal to 0. I'll have minus 10 cosine theta plus in A equals 0. So still have the same number of unknowns. Now I have 2 equations. Right? So now I'm going to have to go over and look at block B. Okay. So at block B, the sum of the forces in the x has to be equal to 0. So that looks like negative the force of the spring plus 0.25 in B minus 6 sine theta equals 0. I introduced a new variable there, so now I have 4 unknowns. So I have to do one more. Sum of the forces in the y equals 0. So I'll have NB minus 6 cosine theta equals 0. Okay. And now I think I have 1, 2, 3, 4 unknowns, but I have 4 equations. And I can solve this set of 4 equations simultaneously. Yes, let's do it. What do you get? if you're putting this into a solver, you're going to have to bound your theta value to be between 0 and 90.
How do you do that? Yeah, some program way to do it.
How do you do that?
Done it in the past. I can't remember how.
Yeah, I've done it in the past, but also can't remember how. Try it without bounding it and see what you get.
That's funky. Yeah, I'm getting really stuck because I can't bound too.
Just don't give us one like this.
Yeah, I'm getting stuck to like ampersands and
Yeah, you get some ampersands that will tell you
and pi
the at symbol.
and things I don't
Yep.
know what to do with.
Okay,
Let's do it by hand.
No.
I mean, how'd you guys have to do this stuff in the past?
by hand.
I
Yeah.
have a whole free page.
Yeah, but I don't want to waste the time to do this by hand. Let's look and see what the interwebs tell us for bounding an equation on a TI-89. Don't like that. There it is. Looks like you use the straight up and down symbol on your 89. So you do like comma, then you have the X. You'd close it and then do straight up and down x greater than equal to 0 and x less than or equal to 90.
What?
This says 2 pi, but they're in radian mode, so we would want it in less than or equal to 90 in our problem.
What is the symbol for less than or equal to 90?
You should be able to get it.
Oh, right, I have a less than, but...
Yeah, you can do less than, that's fine. That's the 0 or the decimal on the calculator.
I literally haven't had to do this since like 12.
Okay. So you can look up how to do that. Be good to know for moving on. But yeah, I think the question for this problem was more around how do you solve, friction problems like this, and this is how you solve it. If you got to this point on an exam, you'd get a 7 out of 10, right? You just need to fill those in. Okay. It was asking us to find the angle theta at which they start to slide, and then the deformation of the spring. So once you know the force of the spring, pretty easy to find the deformation, right? Because F equals Ks. So we know K, we know the force, so then we can just solve for S. Okay.
There's a nice way to do it. We've done it in physics.
Okay. All right, so I think we've hit everything in the packet now. Things that, the packet was heavier on early stuff because we've just recently gone through, shear moment diagrams and friction, right? I didn't put any friction in the packet because that's what we just done. Friction will be on the exam, to be clear, right? So here's the things, and you keep me honest. Here, I'm going to make a list of the things that I think I've guaranteed to you to be on the exam.
Friction.
One is a shear moment diagram.
The triangles you said.
Yep. Shear moment diagrams with sloped distributed load. 2, I think I've guaranteed that you will have a machine problem. Okay. 3, I think I just guaranteed that you'll have a friction problem on there. So that could be a wedge. It's not going to be a screw, right? So it could be a wedge, it could be a block. Could be something along those lines, okay? But there will be a friction. So a friction problem, I'm not going to tell you whether it's type 1, 2, or 3, right? So type 1 is not close, not moving. Maybe it'll be one where you have to figure out what type it is. Type 2 is on verge of moving. So F force of friction equals F max. And the third is sliding. All right? So then the force of friction is equal to force of friction kinetic, right? So remember also there's that whole tipping issue we need to resolve, whether it tips when it slides or whether it just slides. And we do that by, if we have a box like this and we're putting some force on it up here, we check to see, remember the normal doesn't have to be right in the center, and we check to make sure we sum the moments with x. Let me do a new one. This is the box, and I put my normal force here, and this is my pushing force. If I want to check to see if it tips or not, I can sum the moments about this corner, where x is right there, right? And we see if x is positive, it's not going to tip, right? If x has to be negative in order for it to stay upright, then we know it would tip. Okay, it's a pretty easy check to do there. And what's missing from my free body diagram here that would be important in figuring this out?
Friction.
Nope, friction wouldn't be important because it runs through my point. The weight of the box, right? My W there. So essentially we're seeing if the pushing force can overcome the weight moment, and if it can, then we know our normal would have to be over here to help keep it from tipping. Therefore, the moment can't be over there, it's going to tip. Okay? So you can sum the moment about here. These are, I kind of like these problems because for friction, because they make you evaluate all three cases. That it's not moving, that it's on the verge of moving, or that it's sliding and does it tip. Okay? So these are probably common final problems. I'm not guaranteeing it. I want to leave some freedom of expression for me on my artistic masterpiece of a final that I make. Okay? But don't roll your eyes at me, Victoria. Right? So
Just like reuse old ones.
no, I don't reuse old ones. I make new ones
every time?
every time. Absolutely. Okay, so tipping problems are nice, but I'm not guaranteeing it. I am guaranteeing friction. And what this will be, I'm going to call this Andy's choice for the rest. Okay, Andy's choice.
On Wednesday, do we see distributed load as well?
Yeah, but that'll be.
That, I mean, shear and moment diagram will have a distributed load, so yes. Maybe it'll appear other places. Maybe I'll put a friction problem with a distributed load, or who knows. But so other things that come to mind in Andy's choice is a truss, right? You need to know truss problems. So I probably want to see that you can do method of joints or method of sections, right? That is in Andy's choice bucket. I'm not saying that I'm doing it, right? But trusses seem like a likely candidate. Static equilibrium, that's a classic that you got to know, right? You didn't do very good on that on the midterm either, but I think you should be able to now, right? We've done some of them. I'm not trying to be mean in saying that. I'm just saying areas where you've struggled in the past, I'm going to probably ask again to see if competency in. That's all I'm saying. I'm not trying to be critical. I'm sorry. Okay. Yep. Me too. Okay. Flip through here. Yeah, moments, maybe three-dimensional moments or cross-product moments, right? Those are moment about a specified axis. Like those are good ones that should be gimmies, right? the cross product moments, I might do one of those like right in the beginning for a nice warm up for you of just like, yeah, I can own this exam, right? Just take a cross product. You can do that. Okay?
That's it. That's the test.
So if you look at this, when you're studying, I'd like you to look at this until you say, okay, shear and moment diagram with a slope, I know exactly what I need to do, right? That's kind of like when you know if you've studied enough is, do you know exactly what you need to do when you see this? Do you know what you need to do when you see a machine problem, right? Do you know what you need to do when you see a friction problem or trusses or static equilibrium or moments? Just if you have a general confidence in all of these, right? If you can demonstrate to me that you know what to do on the final when I present these problems to you, you will get a passing grade on the final, right? So calm down, don't stress out, right? This is still a lot, but if on the final you can demonstrate to me, I knew what to do in each one of these, and maybe I flubbed up a calculation or something like that, you know, fine. But if you show me you know what to do when you get to each of these problems, you'll pass, right? I think my grading has shown that. It's only when you like completely go down a wrong path that you really get less than 7 out of 10 on a problem, right? So you have to really like say, oh yeah, trusses, I can cut that in a spot and solve for 4 things independently. I'm like, yeah, you clearly didn't listen, right? Okay, like I'm not trying to be mean, but I'm just saying that's a clear indicator to me you haven't got the content down, right? Or yeah, or shear and moment diagrams, you know, going kind of off the wall. If here's a dead giveaway for me, actually, be really sure that your shear diagram result and your moment diagram that they line up, right? So remember that if you have a shear diagram that has a positive value in an area, you should have a positive slope in that area, right? And if it should cause a positive change as you go across, because that's, for me, that's something I'll look at. If you don't have the right answer, the very next thing I look at is, do their graphs agree with each other, right? Maybe they got the wrong calculations, but do they at least understand that the relationship between the shear diagram and the moment diagram? Does that make sense? Okay. Those are things that I look for as I go through. Static equilibrium. Do you know what to do once you find the unit vector, right? On the midterm, lots of you didn't. You could find the unit vector and then you got stumped on what to do with static equilibrium. So you need to take that unit vector, multiply it by the unknown force along the line, and then sum the forces in the x, y, and z, right? So those for me are kind of where I say, is this a passing grade or not? Did they have the right idea? Maybe they got the wrong unit vector, but they multiplied it by a force vector, and then they went through and did some calculations and summed them in the x, y, and z. That to me is passing. You screwed it up, but you knew the right way to do it. Now, if you just found the unit vector and didn't know what to do after that, that's not passing. You don't know how to approach that problem. Okay? So just trying to explain a little bit of like how I approach grading these. Okay?
Are we still gonna have an hour and 20 minutes?
No, you'll have hour and 45 minutes. Yep. So it'll be from 10 to 11:45. Yep. I don't know how many questions the exam will be yet, right? If I do small little ones, it could be more than that, but it'll be more than 4 and less than 10.
More than 4, less than 10?
More than 4 and less than 10.
That's fine.
Okay. Choose a number.
As long as you want a grade.
I don't know. Depends on how difficult they
How
are.
many students, but
Right.
how many problems?
All right. Well, that's statics. Have a good break. Don't start yet. Break, just to be clear, starts after Monday. Okay?
And about all our other finals, they don't matter.